Solving chemical problems. We do a lot of problems in chemistry. And one of the most common problems we need to work on is unit conversions. Using units as a guide to solve a problem is a technique called dimensional analysis, and hopefully you're all familiar with that. I'll be going over it fairly briefly. If you need more help with that, please see me. It's very important that units are included in all of your calculations. We multiply and divide them and cancel them like any other variable. So if you had x and y and you were multiplying, you'd end up with xy. If you have meters and seconds and they're being multiplied, you'd end up with meter seconds. Oh, my computer's not responding to me. So when we convert units, we make use of what is sometimes called a unit equation. This is a statement of two equivalent quantities. For example, 2.54 centimeters is equal to 1 inch. There are different ways of describing the same quantity. 1 inch is the same as 2.54 centimeters. We can make a conversion factor from this statement, and we do so by dividing both sides by one or the other. So let's look at how we would do that. 2.54 centimeters equals 1 inch. Well, if I divide both centimeters by 1 inch, this is still an equality because I did the same thing to both sides. On the right side now, inches over inches equals 1, and 1 over 1 equals 1, and so this is equal to 1. 2.54 centimeters over 1 inch is equal to 1. If I multiply something by 1, does it change its value? No, it doesn't. So I can use this factor to convert units without changing the actual length. I can do it like that, or I can tip it over and have 1 inch over 2.54 centimeters. That is also equal to 1. Most unit conversions take the following form. You have information that's given, and there's information that they're asking you to find, and then you're going to apply one or more conversion factors in between. So it's the given unit times a factor where you have the desired unit on top and the given unit on the bottom. The given units cancel out, leaving you with the desired unit. Let's do an example. How many centimeters are in 12 inches? So we are given 12 inches, and we are asked to find how many centimeters. I like to make a path. It's hard to get somewhere if you don't know where you're going and where you're starting. So by writing down what I'm starting with, my given quantity, and my desired unit, where I'm going, I'll avoid being lost in between. This is a very simple example. We don't really have to have a path, but some of them will become a lot more involved, and you'll be very thankful that you have a path. So what I'm going to do is I'm going to write 12 inches. I'm going to look at my path. This path has one arrow. I'm going to use one conversion factor, and that's going to equal something. I'm going from inches to centimeters. In my equation, I have inches here, and I'm going to have centimeters on the numerator on the top of my conversion factor, and I'm going to put inches in the denominator because I want the inches to cancel out. After I get the units in place, then I put the numbers in. I need to know the relationship between inches and centimeters. Well, we covered that. 1 inch is equal to 2.54 centimeters. The number with inch is the number 1. That number has to stay with its unit. So I get 1 inch on the bottom, and I get 2.54 centimeters on top. So this is on the top, and this guy is on the bottom. One side of the equal sign will be on the top, one will be on the bottom. The unit you're starting with, the unit you're going to, tells you where to put those units. What's very important is that the top quantity is equal to the bottom quantity. 2.54 centimeters is equal to 1 inch. Now I just do the math on my calculator. I've got 12 times 2.54, divide by 1 if you like, and I get 30.48 centimeters. How many significant figures should that answer have? 2. This number, 12 inches, has how many significant figures? 2. It's a whole number, but it's not a counting number. So this has 2 sig figs. And how many does this number have? Infinite. That is a defined quantity. So we started with 2 sig figs, we end with 2 sig figs, and this is going to be 30 with a decimal point centimeters, or better, 3.0 times 10 to the 1 centimeters. That's the best answer. Any questions? So here's the general strategy. Figure out what you're starting with. What's being given? Identify the end point. What am I trying to find? And then you have to figure out how to get there. Did you guys ever watch Dora the Explorer? Or perhaps you have younger siblings or children. Watch Dora the Explorer. She was always trying to get from one place to another in her cartoon kingdom. And she would say, who do you ask when you don't know which way to go? The map. And the map would come out of the backpack and tell you, well, if you want to get to the snowy mountains, first you have to go over the troll bridge, then you have to go through the scary woods, and then you get to the snowy mountains, right? Then they would chant it several times so that they could remember. So this devise a way, this is the figuring out, how am I going to get from where I'm starting to where I need to go? Sometimes it's very simple, sometimes it's more challenging. But you have to come up with a plan or a path. Another organizing idea is sort, strategize, solve, and then check your work. Does your answer make sense? If you're doing a big old calculation and you come up with an answer that's 0.02 atoms, can you have 2/100ths of an atom? Atoms are indivisible. That's like saying, doing a calculation and finding that the average family size is 0.3 people. Could that be correct? The average family size? No, 1 is the smallest number that you could have, right? So that tells you, hey, my answer doesn't make sense. I better go back and see what happened. Let's do some examples. Convert 288 centimeters to yards. So these are nice word problems. They don't have very many words. There's only one number in this problem. So that must be where we're starting. 288 centimeters, and then we'll leave some space, and we're trying to get to yards. The path that you take depends on what conversion factors you either know or have available to you. If you can look up a relationship between centimeters and yards, you could do this in one step. I don't know what that number is. So you might think, okay, well, we've got centimeters and we've got yards. We need to go from metric to English somewhere. I know the relationship between centimeters and inches, so I could go from centimeters to inches. Yeah, you could go inches to feet and feet to yards. And some people might say, well, I know how many inches are in a yard. I'm going to skip that, and that would be fine. But we'll do this one. So we've made up this path, and each of these arrows represents a conversion that we know or can look up. The relationship between centimeters to inches, inches to feet, feet to yards. That's our path. It's going to tell us where to go. So I write down 288 centimeters. I look at my path. There are 3 arrows. I'm going to have 3 conversion factors. The units in my path become the units in the numerator. This is like Dora chanting centimeters to inches to feet to yards. And then you come down here and you write centimeters to inches to feet to yards. The units in the denominator come from the previous term. I'm starting with centimeters. I want those to go away. So I need to divide by centimeters. Centimeters divided by centimeters cancels out. So I want centimeters down here because those will cancel out and go away. I have inches here. I need it to go away, so I'm going to divide. Inches cancel out. And then I write feet down here, and the feet will cancel out. The unit that's left is yards, and that's what I was trying to find. This is dimensional analysis because you analyze and solve the problem based on the dimensions, the units. The units tell you what to do. This is a very, very important technique. In examples like this, you may say, oh, well, I don't need to go through all that. I can do that easier. That's fine. But when we get to stoichiometry and you're converting grams of oxygen into grams of hydrogen or liters of hydrogen, the way you do lengths isn't going to work, most likely, because these are kind of strange quantities that you're not familiar with. We got all the units in, now we need numbers. Well, let's just do the middle one first, just for fun. What's the relationship between feet and inches? 12 inches and 1 foot. So 1 foot, and there's 12 inches. How about yards and feet? 3 feet is 1 yard. And then we've done this one a couple of times today. 1 inch is 2.54 centimeters. Now, if we put the 12 on top, bless you, and had 1 on the bottom, we'd have 12 feet equals 1 inch. Is that true? No, it's ridiculous, isn't it? 12 feet is a really, really long distance. It's more than 1 inch. You have to get the unit with its number. To do this on your calculator, I recommend that you just start at the left side and go across. 288 times the top, divide by the bottom, times the top, divide by the bottom. Of course, multiplying and dividing by 1 doesn't change anything, but some students feel more comfortable putting it in there. They're like, no, I just need to follow the pattern. That's fine if you do that. Personally, I don't enjoy multiplying by 1. So I'm going to do 288 divided by 2.54 divided by 12 divided by 3 equals. And then my calculator gives me this big long answer, 3.149606299. The unit is yards. And now that we know about significant figures, we can practice that. How many significant figures should the answer have? 3. The starting number had 3 significant figures. Each of the unit factors here is an exact conversion. Exact conversions do not change the number of significant figures. So we're going to say this is 3.15 yards. Any questions? There's a technique called the bigger, smaller rule. If we look at centimeter and yard, which is the bigger unit? Which is longer, a yard or a centimeter? A yard. So the bigger unit, yard, should have the smaller number. The smaller unit should have the bigger number. A common error is students get their numbers upside down, and then it gets bigger instead of smaller, or vice versa. So looking at the bigger, smaller can help you catch an error. Do you want another example? Okay. Sure, why not? Convert 9255 cubic centimeters to gallons. Well, we identify what we're starting with. It's the only number, 9255 cubic centimeters. And we're going to gallons. We have to figure out how to get there.
Centimeters squared to milliliters, milliliters, liters, liters to gallons.
Yeah. We could do cubic centimeters to milliliters, milliliters to liters. We need to be able to find. It is. It is. Cubic centimeters to milliliters is a 1-to-1 conversion. Liters to gallons. Can somebody look up the relationship? Because I don't remember that one off the top of my head.
785.
Not guessing, you got to look it up.
0.26.
0.26?
417 gallons to 1 liter.
0.2641
417.
liters is 1 gallon?
That's gallons.
Gallons is 1 liter. Okay, thank you. Okay, so the path you choose here is going to depend on what you have available to you. But we found that one, so we can do this path. As one student pointed out, cubic centimeters to milliliters is a 1-to-1 conversion. I'm going to go ahead and write the whole thing out, but it's perfectly fine to just cross out the cubic centimeters and write milliliters, because they're two different names for exactly the same thing. So if you're comfortable doing that, you go right ahead. 9255. How many arrows in my path? 3. So I need 3 factors. Cubic centimeters to milliliters to liters to gallons. Copy that in the numerator. In the denominator, we're going to have the previous unit, because those will cancel out. We want all these units to go away except for gallons at the end. Milliliters down here, liters down there. Now we put numbers in. This is the one we looked up, so this number goes with gallons, 0.26417, and that is equal to 1 liter. Liter to milliliter. This is a metric conversion with prefixes. We need to know that milli is 10 to the minus 3. I have milli in the denominator. I'm going to write its numerical equivalent on the other side. 10 to the minus 3. So you might look at that and say, that's going to be messy putting it in my calculator. Well, how about 1 times 10 to the minus 3? That's the same, isn't it? Now that looks like scientific notation, and we should know how to do that. Some people want a 1 down here, that's fine. And then this is 1 milliliter to 1 cubic centimeter. 9255 times, if you're rusty on the scientific notation, it's going to be 1 EE or EXP minus 3, and then times 0.26417. I think it's a good idea to write down everything that your calculator gives you and then round it off. I think it's better to write too many figures than not enough, because you can always go back and chop them off if you realize, oh shoot, I did that wrong. If you round it off too far, and you realize you did it wrong. You have to go through and do the calculation over again. So how many sig figs should this answer have? 4. This number has 4. This is exact. This is exact. This is not exact. But 0.26417 is 5 significant figures. So we should have 4. It's going to be right there. So we'll say 2.445 gallons. Let's do the bigger, smaller test. Which is larger, a cubic centimeter or a gallon? A gallon. So gallon should have the smaller number, cubic centimeter should have the larger number, and it does. Any questions? Sometimes we have units raised to a power that we have to convert. What you're going to do when this happens is you're going to use the same conversion factor as for the unit without the power, but you have to raise the number to the power as well. So 2.54 centimeters is equal to 1 inch. If we square both sides, that's still equal. 2.54 centimeters, the quantity squared is 2.54 squared times centimeters squared. Over here, this is 1 squared times inches squared. Well, 1 squared is just 1. That's easy. So we have 1 inch squared is equal to 6.45 square centimeters. So let's look at a picture. So I'm going to draw a square, and it's 1 inch on a side. What is the area of this square in square inches? 1. It's 1 inch times 1 inch. This is 1 inch squared. Great. Well, this is equal to 2.54 centimeters. And this side is also 2.54 centimeters. So the area is equal to 2.54 centimeters times 2.54 centimeters, which will be 6.45 square centimeters. The frequent mistake is students forget to square the 2.54. This area is not equal to 2.54 square centimeters because it was 2.54 on each side, and so the number has to be squared also. If it's cubed, you have to cube the number. Let's do an example. How many cubic centimeters are there in 2.11 cubic yards? Well, we identify where we're starting. 2.11 cubic yards, and we're trying to get to cubic centimeters. Well, how should we go? Ignore the cube at first. How would we go from yards to centimeters? We could use yard to feet to inches to centimeters. Or let's take a shortcut this time. Let's go from yards to inches to centimeters. How many inches are in a yard? 12 times 3, 36. So we could make that little shortcut. What I'm going to do when I write out my equation here is I'm going to ignore the power, the cube, at first. And I'm going to go yards. I have 2 factors. It's going to be yards to inches to centimeters. And I'm going to have yards down here, and I'm going to have inches down there. And now I want to put my numbers in. 36 inches to 1 yard, 2.54 centimeters to 1 inch. But this is cubed. This is yards cubed. So what I'm going to do is I'm going to take this whole conversion factor and cube it. And I'm going to take this whole conversion factor and cube it. Do not cube the 2.11. People get carried away and do that. This is 2.11 cubic yards. We don't need to cube that. But 1 yard equals 36 inches, and if we cube that, we have to cube everything in there. Some people might find it helpful to write it out in more detail, perhaps writing 36 cubed inches cubed over 1 yard cubed. And here's 2.54 cubed centimeters cubed over 1 inch cubed. Whatever works for you. You can also just put the conversion factor in there 3 times, if that makes more sense to you. Some ways are faster, but in the story of the tortoise and the hare, the tortoise always wins, right? Slow and steady, and he just keeps going. So when I do this on my calculator, I'm going to do 2.11 times 36, and then I have an X to the something button. And I'm going to press that and cube my 36. And then I'm going to multiply by 2.54, and I'm going to use that button again. And I'm going to come up with a big number. Are we expecting a big number? Yeah, we are. 1613210. Sorry, it's going off to the side. 75 cubic centimeters. Anybody else get that?
Yeah.
That's got way too many digits. How many sig figs should that answer have? 3. Again, it's our starting value that's going to limit. You'll see that that's often the case. 3 sig figs. So I'm going to keep the 1, the 6, and this 1. I need to be careful. Question?
Why wouldn't it be 2 sig figs if it's 36 inches?
That's a good question. There's 2 sig figs in 36. But 1 yard is exactly 36 inches.
Exactly.
Yeah. So here I am rounding in a place far to the left of the decimal point. I do not want to round this off and call it 161 by mistake. So the best thing would be to put it in scientific notation first and then round it off. And I've been writing so large, I don't have room. I'll write it way up at the top. 1.6. 1, 3, 2, oh, that's plenty, isn't it? Times 10 to the, right here, 1, 2, 3, 4, 5, 6. And I want to keep this, so I'm going to say this is 1.61 times 10 to the 6 cubic centimeters. Because 1.6 million cubic centimeters is very different than 161 cubic centimeters. Any questions? Do you want me to do this example? You feeling pretty good about things, or you know, let's skip this. Well, let's do this one though. This one's a little different. Density is a conversion factor. Typo. Backpackers often use canisters of white gas to fuel a cooking stove's burner. If one canister contains 1.4 liters of white gas and the density of the gas is 0.710 grams per cubic centimeter, what is the mass of the fuel in kilograms? Well, this is a bit of a leap, isn't it? Let's pull the numbers out. Let's figure out what are we starting with and what are we trying to find. There are 2 numbers in the problem. Let's write them down. 1.45 liters, 0.710. This is written with a slash because it's easier to type. But when you write it down, write it as a vertical fraction. Grams over cubic centimeters. That way, you're pointing out to yourself, this is a fraction unit. So we're starting with one of those, and what are we trying to find? Mass. What is the mass of the fuel in kilograms? So we're trying to get to kilograms over here. We have to decide which of these units do we start with. This one is a single unit, this one is a derived unit. Usually, the single unit is where you start, and you'll end up using this as a conversion factor. That relates mass to volume. You can do this using the density equation. And if you're good at that, you go right ahead. I don't need to show you how to do that. But lots of people, when they do that, they get things upside down and backwards. You can use dimensional analysis. So we're going to save this as our conversion factor. And we're going to go from liters, and we're trying to get to kilograms. And it's probably not obvious what we're supposed to do here. Let's look at our density here and see if it's related to anything. How about grams and kilograms? We know how to do that. So if we got to grams, we could go to kilograms, no problem. And this has grams in it. This would allow us to go between grams and cubic centimeters. So we're working backwards, that's fine. How about cubic centimeters to liters? Milliliters are in there, right? Milliliters, and we know the relationship between milliliters and cubic centimeters. So we figured out the path. That's the hard part. Once you figure out the path, you just follow the pattern and do the calculation. 1.45 liters. We've got 1, 2, 3, 4 factors. Liters to milliliters to cubic centimeters to grams to kilograms. There are multiple ways to get from this start to this end. It's a little bit like crossing a river on stepping stones. There's some rocks and boulders in the stream, and some people can jump farther than other people, and some are very cautious and want to take just little steps. But you think ahead of time, oh, if I go here and there, I can get across. And 5 people might choose 5 different ways. Now I put my units in the denominator so that they'll cancel out. A unit in the numerator cancels a unit in the denominator. Then I put my numbers in. Here's our density. This relates grams and cubic centimeters. 0.710 goes with grams. So over here where I have grams and cubic centimeters, I have 0.710 grams per cubic centimeter. If you want a number down there because it bothers you without, it's a 1. Kilograms to grams, we need to remember what kilo means. Kilo means what? 10 to the 3. There's the polite Amtrak train. So here I have kilo in the numerator. I don't want to double that. I don't want to put 10 to the 3 and kilo together because they mean the same thing. I need the top to be equal to the bottom. So if kilo's on the top, I'm going to write what it means on the bottom. So that would be 1 times 10 to the 3rd grams is equal to 1 kilogram. Centimeters cubed to milliliters, we've done that one, it's 1 to 1. And then here we have another metric prefix, milli. Well, milli means 10 to the minus 3. I have milli in the numerator, I put what it means on the other side. 1 milliliter is 1 times 10 to the minus third liters. If you are comfortable with writing 1,000 milliliters equals 1 liter, you go right ahead and do that. But I'm just going to do it this way and be consistent. Now we just multiply and divide across. 1.45 divided by 1 EE minus 3 times 0.71 divided by 1 EE3 equals 1.0295 kilograms. How many sig figs should I round my answer to? 3. My starting number, my volume in liters, has 3, and the density has 3. The others are exact. So that's going to be 1.03 kilograms. Any questions? Do you need to see another one? I think we're okay. Order of magnitude estimations. This is useful and great and everything, but since we're short on time, I'm not going to go over it. You don't have to learn how to do this. It's a nice thing to learn, but it's not really necessary. Some problems involve equations instead of conversions. And usually what happens is the equation has multiple variables and they give you numbers for all of them but one. Then you rearrange the equation and you find the answer. Students usually don't have too much trouble with those. We'll do this example and then we'll call it a day. Find the radius of an aluminum cylinder that is 2.00 centimeters long and has a mass of 12.4 grams. So they give us this equation. So let's write down the numbers that they gave us. 2.00 centimeters, 12.4 grams. Then we have this equation. Volume is pi r squared times L. We need to identify what those numbers are. It says 2.00 centimeters long.
So we have the L.
That's the length.
And volume, I imagine that we probably find out by using the mass.
Yes, we can. So they're asking us for R. They gave us L, but we also need V, volume. And what did they give us? They gave us mass. Did they tell us what the cylinder is made out of? They did. We can look up the density. See, this is where a 1A problem is different than a 3A problem. So we have to go back to density. I really should write this on the slide. Aluminum, 2.70. Density equals 2.70 grams per cubic centimeter. So we need the volume, and then we can rearrange this equation and find the radius. So let's find the volume using dimensional analysis. We can go from the mass, we can go 12.4 grams to cubic centimeters because we know the density. So 12.4 grams, we want to multiply by cubic centimeters and divide by grams. The density, 2.70, goes with grams. That's on the bottom. 1 centimeter on top. 12.4 divided by 2.7 equals 4.59 259, and some other stuff. If we were stopping here, how many sig figs?
It should just be 3.
3. So that would be right here. But we don't want to round this off yet. We want to keep at least 2. I happen to write down 3. That's at least 2. I'm just going to go with that. So cubic centimeters, that is the volume. Now we need to take this equation and rearrange it. We need to solve for R. So I am going to divide by pi so that pi cancels out, and I'm going to divide by L so that L cancels out.
So it would be divided by pi and L.
Yeah, if I do it to one side, I have to do it to the other side, because for it to stay equal,
We have to square root it.
yeah, we do. So now we've got R squared is equal to this, but we want R. So to undo the square, we take the square root. So we're going to end up with R being equal to the square root of V divided by pi times L. So now we put all the numbers in, 4.59259, including their units. Here we have pi. We're just going to use the pi button on our calculators. And then the length is 2.00 centimeters, and the square root of the whole thing. Centimeters cubed divided by centimeters is what? Centimeters squared. And then we take the square root and we'll end up with centimeters. So 4.59259 divided by pi and divided by 2. And then I'm going to take the square root of that. And I'm going to come up with a radius, 0.854946 centimeters. Anybody else get 0.85? How many sig figs? 3. This one has 3. We underlined that one to help us remember. And this one has 3. Pi is a lot more than 3. It's not exact, but it's more than 3. So 0.855 centimeters. Any questions? There's your review.